Welcome to this explainer. Today, we're going to build a foundational mental map of the entire machine learning landscape. Cutting right past all that hype and those endless buzzwords to see how this incredibly cool technology actually works beneath the surface. So, if you've ever found yourself wondering how exactly algorithms make sense of our world, well, you are definitely in the right place. Let's get into it.
We're going to tackle this vast landscape step by step. We'll start with what machine learning actually is, then compare it to traditional coding, look at the different types of ML systems, explore how these machines actually learn, and finish up with a practical workflow you can use.
Okay, Section 1. What is machine learning? Let's define the fundamentals.
To kick things off, computer scientist Tom Mitchell gave us this highly technical definition way back in 1997. He basically stated that a computer program learns from experience E with respect to a task T and a performance measure P if its performance on that task improves with that experience. Wow, okay, while that is technically accurate, we really need to bring this down to earth to truly grasp what's going on.
Simply put, machine learning is the science, and honestly, it's kind of an art too, of programming computers so they can learn directly from data. Right? Instead of us handing the computer a super rigid set of instructions, we give it an experience. Usually that's just a massive data set. That experience could be, say, thousands of past examples of spam emails or thousands of images of cats and dogs. The system literally takes that data, hunts down the hidden patterns, and figures out how to perform the task all by itself. Moving on to Section 2, Traditional Code versus Machine Learning. To really understand why this data-driven approach matters so much, we're going to tackle a classic issue, the spam filter problem. Just imagine the stark contrast in effort here. In a traditional programming approach, you'd have to sit down, manually examine what spam looks like, and write a specific hard-coded rule for every single pattern. For example, if spammers use the word for you with a number 4, you write a rule to block it. But what happens when they get sneaky and switch their tactics to for you spelled out? Well, your traditional program fails, and you have to go right back in and write another rule. It's an exhausting, never-ending game of whack-a-mole that is incredibly hard to maintain. But compare that to machine learning. An ML model automatically learns which combinations of words predict spam, just based on the examples you feed it. So when those spammers inevitably change their tactics, the ML system automatically detects the new patterns and adapts. No human intervention needed. The result? Shorter code, way easier maintenance, and honestly, vastly better accuracy.
All right, Section 3, the types of ML systems and how supervision shapes learning. We generally classify these systems based on just how much supervision the machine gets during its training phase.
So, the crucial point here is that supervised learning is exactly like having an answer key. The machine is explicitly given the correct labels right alongside the data. Thinking back to our spam filter, the training set would include thousands of emails that have already been perfectly labeled by a human as either spam or ham, which, by the way, is just the industry term for a normal, good email. The algorithm uses this perfectly labeled answer key to learn how to precisely map inputs to those known outputs.
Within this supervised category, we usually ask the model to do one of two things. The first is classification. This is all about predicting a specific discrete category, spam or ham, cat or dog, fraudulent or legitimate. The second task is regression, where the goal shifts to predicting an exact numerical value. A classic example of regression would be predicting a used car's price based on input features like its mileage, its age, and its brand.
But what happens when we take away those perfect answer keys? Enter unsupervised learning. Here, the training data is completely unlabeled. The system has to discover hidden structures entirely on its own, sorting through messy, chaotic data streams to somehow find order. In this case, the machine is basically acting as a detective, finding patterns without a teacher ever telling it what to look for.
And this unsupervised approach is incredibly powerful out in the real world. For instance, we use it for clustering, like automatically grouping your blog visitors by their reading habits, even if you have no idea who they actually are. It's also used for anomaly detection to catch sudden, weird outliers. Think of a completely uncharacteristic credit card purchase triggering a fraud alert. And then there's one of my personal favorites, association rule learning. This is where algorithms comb through massive data sets to find surprising relationships, like a supermarket discovering that people who buy BBQ sauce also have a massive tendency to buy steak. Once you know that, you can literally rearrange your product placement to boost sales.
We also have some truly brilliant hybrid approaches. First up is semi-supervised learning, which deals with data that's only partially labeled. Think of Google Photos. It automatically groups all the photos of the same person together using unsupervised clustering, right? And then it just asks you to provide one single label, the person's name. Suddenly, boom, thousands of photos are neatly categorized. Then we have self-supervised learning. This actually generates a fully labeled data set from a completely unlabeled one. And fun fact, this is actually the magic behind those massive large language models we hear so much about today. They take huge amounts of normal text, mask random words, and literally force the AI to predict what's missing. The original unmasked text just acts as the answer key. Pretty clever, right?
Our final type is reinforcement learning, and this is just a fascinating continuous loop. In this setup, the learning system is called an agent. It observes an environment, selects an action, and then gets either a reward or a penalty in return. Over time, it learns a policy, which is basically a master strategy of what actions to take to maximize its total reward. This is exactly how robots learn to walk without falling over, and it's precisely how DeepMind's AlphaGo analyzed millions of matches to completely master the incredibly complex board game Go.
All right, section 4. How machines actually learn. So we know the types of supervision, but now we need to look under the hood to understand the actual mechanics and learning approaches these systems use to ingest data and make their predictions.
A system can ingest data in two main ways. First, it can be trained on all available data at once, completely offline. This is known as batch learning. You train it, you launch it, and it just applies what it learned. The big risk here, though, is something called model rot. Its performance decays over time because, well, the real world evolves while the model stays fixed, so you have to constantly retrain it. Alternatively, it can learn incrementally on the fly as new data arrives. This is known as online learning. It's fast, it's cheap, and it adapts beautifully to changing environments, although you do have to monitor it pretty closely to make sure a sudden stream of bad data doesn't just corrupt your whole system.
Now, when it comes to actually making a prediction on a new piece of data, the machine basically has two choices. It can either compare the new data directly to a massive bank of memorized examples. That's called instance-based learning. It's kind of like saying, hey, this new email looks a whole lot like those 5 spam emails I already have memorized, so it must be spam. Or, on the flip side, it can actually build a mathematical equation to make super fast predictions. That's model-based learning, where it figures out the perfect parameters by minimizing what's called a cost function.
To ground this model-based approach in reality for a second, imagine we want to predict a country's life satisfaction based purely on its GDP per capita. If we feed our algorithm a bunch of historical data, it builds a linear model. Then if we input exactly $33,442, which is Puerto Rico's GDP, the mathematical model instantly crunches that number and spits out a life satisfaction prediction of 6.02. And amazingly enough, that prediction proves to be highly accurate when you compare it to the real-world data. It's like magic, but it's just math.
Section 5, the machine learning workflow. Let's put it all together. Now that you've got a solid grasp on the entire theoretical map, let's look at how you'd actually build one of these systems step by step.
If you're ever going to build your own ML project, you're pretty much always going to follow this iterative 4-step cycle. First, you thoroughly study the data to identify patterns and potential issues. Second, you select a model architecture that actually fits your problem. Maybe that's a linear regression, or maybe it's a deep neural network. Third, you train the model by running the algorithm to find the absolute best possible parameters. And finally, inference. That's where you apply that newly trained model to unseen cases out in the real world. And hey, if the predictions turn out to be poor, you just loop back. You go get better data, you pick a more powerful model, and you train it all over again.
And that brings us to the end of our map. The big takeaway here is that machine learning is uniquely equipped to handle complex problems that have absolutely no known mathematical solutions. It thrives in rapidly fluctuating environments and tears through massive datasets that are hiding invisible insights. So I want to leave you with a question. Looking at your own industry, your own hobbies, or your personal passions, what complex problem, one that currently requires endless, exhausting manual rules, are you going to solve using this incredibly adaptable framework? Take some time to think about it. Thanks so much for joining me on this explainer, and keep learning.